Hello, everyone. Welcome to the afternoon edition at Biddle Squad stage in the Biddle Hub. My name is Jane Harrell. I will be your MC for the rest of the evening. And first up, we have Chris Smith from Spearbit, and he's going to be talking about ERC-6492, security risks and safe implementations.
How is everyone doing? Let me see if I can get this to be full screen here, or as close to it as possible. Okay, excellent. So, as Jane said, my name's Chris Smith. I am a security researcher with Cantina Spearbit. I'm one of their fellows. In that role, I get to see a lot of different code patterns, a lot of different projects, and one of the interesting security considerations that I came across was ERC-6492. So I thought I would talk about what that is and some of the security considerations that go into it. I'm going to use a hypothetical smart contract system, a DApp here, for this to make it hopefully a little bit simpler so that the actual system doesn't get in the way. And then we're going to walk through what ERC-6492 is and some of the attacks and potential mitigations with it. So first, let's talk about our hypothetical system here. See if I can make my speaker notes a little bit bigger for myself. There we go. Okay, so very simple system. We're going to have a permissioned DApp contract that's going to interact with a user's address, EOA, or smart contract proxy, and that proxy can be launched via a factory. When I say permissioned smart contract, the user's going to grant this DApp some sort of permission on their wallet to transfer funds or to do some admin work for them. This is going to be a common pattern that you see in a lot of dApps where they're having the user authorize their smart contract or authorize the DApp to do something on their behalf. It's a key part of account abstraction because you try to take submitting those transactions away from the user, let someone else handle it. It's a little bit easier user experience and a little easier for the users. As I said, there's going to be a proxy factory. This is just going to deploy the user's smart contract proxy. The important thing with the factory for this is that it's deterministic, so you can predict what the next smart contract address is that's going to come out of there. And as I said, the user is going to give the DApp permission to do something on their behalf. So to understand what ERC-6492 is doing within this system, you first have to understand what ERC-1271 does. So as you saw in the smart contract system that we're dealing with here, we have either an EOA or a smart contract proxy for the user. EOAs can provide signatures so that they can permit the DApp to do something. Smart contracts can't necessarily do that where they provide a signature for a permit function. That's what 1271 solves. So it implements a standardized way for smart contracts to provide and validate signed messages using this isValid signature function. Now protocols can treat smart contracts or EOAs in the same way when it comes to permit or authorization. This helps and opens up possibilities with account abstraction and smart wallets, as we'll see. Okay, 6492 builds on top of 1271. So the problem that 6492 is trying to solve is, as I said, the user is deploying their proxy, or the proxy will be deployed using a factory, and that may not yet be deployed. So now we're dealing with a multi-chain environment in blockchain. Perhaps you have your smart contract wallet deployed on mainnet, but you don't have it deployed on the L2. The DApp goes across both systems, and you want to be able to provide that same experience to your user, same signature, authorization, permit to the user. But their contract isn't deployed on the L2 yet. You want to make it an easy process for them. You don't want them to have to deploy their contract first before they start doing things with the DApp. Some of these dApps require you to sign something just to sign in and use the DApp. So you don't want to make the user deploy the contract that they don't necessarily have yet on the chain in order to do that. That's where 6492 tries to come in. It allows you to have signature permission on deferred deployment contract or deferred contract setup. So the signature when validating the signature, 6492 describes the flow for how you can deploy the contract using the proxy factory, or you can make a call to the user's contract if it's already deployed to set up some sort of authorization. Set up a signer, set up a user, do an approval, something like that. 6492 specifies that in order to do this, you're going to wrap your 1271 signature in a new way. You're going to add either a address for the create to factory and the call data for that, or a prepare to address and the call data for that, and then encode that with the 1271 signature and wrap both of those things, or actually append the 6492 magic bytes code on the end of that signature. And that's how we'll tell that we're dealing with 6492 rather than 1271. All right, so now I want to dive into an implementation. I'm going to use the Solady implementation here from their signature checker lib. This is I love the function name, isValid ERC-6492 signature now allow side effects function in their signature checker lib. Very important note here, this is an older version of the Solady library. They have updated this. This is taken from version 00236. The current version is 019. So they have made a lot of changes to the Solady implementation. I'm using this because it's the one that I came across in the audit, and I think it was a little bit simpler to show how 6492 flow works within the signature checker lib. So let's dive in and look at this code. We'll take it bit by bit. The first bit here is this internal assembly function, call isValid signature. This isn't something we need to dive into too much. It's just the abstraction of how we're going to do the 1271 signature check throughout the rest of the code. So the first substantive piece that the Solady implementation is going to do for us is we're going to check to see if we're dealing with 1271 or if we're dealing with 6492. Sorry, a lot of EIP numbers, they get jumbled. So the first line here, the if statement, is checking whether or not that magic code, this 0x6492, 6492, 6492, on and on and on, is present at the end of the signature that we received. If it's not, so if that value is 0, then we're just doing a regular 1271 validation, and we can call the contract signer with the signature per normal using that function that we just looked at. However, if we do find the 6492 there, we need to do some other things to the signature before we can proceed. So the first thing we're going to do is we're going to find the location of the address. This is either going to be that proxy factory address or the prepare to address. So that's what goes into the O slot here, is the starting location of that address. The D is going to be the call data that we're going to use when we make that call, regardless of where we're going with it. Our if statement here is checking whether or not the signer address has code added. That tells us whether or not the smart contract has been deployed. If it hasn't been deployed yet, then per 6492 specifications, we need to go try to deploy that smart contract before we validate the signature. So if there's a 0 code size at the signer address, then we're going to call the O address, which we assume is the proxy factory, with our call data, check the return. If the return is 0, we assume that call failed, and we're going to break out of the whole function. isValid signature is currently false, so if we break out at this point, we're going to tell whatever application, the DApp in this case, called this, that we don't have a valid function signature, we couldn't deploy the code basically, and that smart contract's probably going to stop doing whatever, hopefully it's going to stop doing whatever it did, and throw some sort of revert. If that call succeeds, then that won't be 0, and we get to proceed to the next piece. So we've checked that we have a 6492 implementation. We've checked that the contract is there. Either it was there already, or we deployed it, and it's successfully there now. We know that we're dealing with a 6492 wrapper situation. We've already grabbed O, we've already grabbed D. Now we need to get the actual signature that we're going to check. So that's what the first line does. And then we're going to just call the signer and say, hey, is this a valid signature? And store that value. If it's not a valid signature, then we want to try that prepare to call and that with the prepare to data, which is what this if call does. Again, it's calling the address O with call data D. We don't check the return here because we're going to go check the signature next, and we're going to override our previous is valid signature. So at this point, we kind of see how the 6492 flow is working. Either we do a 1271 signature per normal, or if the contract doesn't exist, we're going to try to deploy it. Or if it does exist, or we've successfully deployed it, we're going to check the signature per 1271. If that signature fails, we're going to make another call to that O address and then recheck the signature. After that last recheck, we take whatever the result is and move on, return this back to whatever called the library. Some important security considerations about how this is constructed. As you saw when I was talking about the ERC-6492 specification, the prepared to data or the factory data is not part of the actual signature. We're not checking the user's signer that they signed that data and verifying that data. This is just arbitrary data that's wrapped around our 1271 signature. That means that if your DApp is using third-party permissionless keepers that are pulling these signatures for your users from some sort of mempool or something like that, they can pull one, knock this data off, or add their own data around a 1271 signature, and your DApp won't know anything about that. So the prepared to address, the factory address, and the call data that go with these things are effectively arbitrary addresses and arbitrary call data. Now this is very, very important because we've seen kind of the flow of how 6492 works. So let's go back to our system. Remember, the user is setting up some sort of permission or already has set up some sort of permission between the DApp and their smart wallet that's holding some sort of value, presumably, or potentially. They're providing a signature that someone else is delivering to the DApp. Their contract or their EOA is going to check that signature. Many of these proxies have some sort of batch function or multi-call function to help with the user experience of using the wallet or for DApp so that they can do multiple things in one transaction. This is actually a feature for them. It increases security if you want to provide a limited approval and do a transfer in one transaction. The multi-call function in a user's proxy is going to handle that for you. So a lot of these smart contracts have that feature, and you'll see why it's important to point that out as that comes into play later. Again, the factory can deploy the contracts in a deterministic way. This is just rehashing the system that we described earlier. All right, so let's look at the two attacks for this. So for the first one, we're going to make a couple of assumptions. In this case, the user's proxy is already deployed and has the DApp set up with permissions. The user's proxy has some sort of state in it that can be changed by the DApp that will make the signature initially invalid and then later be valid. So we have some sort of state toggle. Let's say like if you're adding a new signer, maybe you have a signature that is for that new signer, your DApp has permission to add that signer to the user's smart wallet. That would be a case where obviously the signature is not going to work the first time, the signer is not added. The DApp makes a call, hey, the signer's there, now the signature works. So that's what I mean by that toggle. So the attack here is we have a 6492 wrapper. We're not going to go through the 1271 flow. Our signer contract, the user's wallet, is already deployed, so we don't need to deal with the proxy factory. We can ignore that. When a signature valid is called, we're going to get false because in the hypothetical, the signer's not set up or whatever about the user's wallet, that state isn't set up in such a way that the signature is going to be valid. So now we have a deployed wallet and a failed signature. In that 6492 flow, that means we're going to make a call to prepare to with our prepare call data. The attacker has replaced or has put in their own call data for the prepared data that is a multi-call for that proxy. The first thing they're going to do, and remember the DApp has permission on the user's proxy here, so the first thing they're going to do is drain all the funds. They're going to send the money someplace that they want it to be, because that's the point of the attacker. The next thing they're going to do is make a call within that proxy such that the state changes so that the signature is valid. So in 6492, signature is invalid, make an arbitrary call to an arbitrary address, check the signature again, hey, it's valid, transaction goes forward, no revert, user doesn't have any money, and the attacker has it all. Second attack doesn't require that state where the user's wallet has a batch function, and it doesn't require the state where the DApp can toggle that signature validity between a false to a true state. This one, again, assumes that the user's wallet has been deployed and the user has set up the permissions for the DApp. So this is, after a user has used the DApp for a little bit, everything's hunky-dory, an attacker comes along, takes that, finds out the victim's address. They don't even need a signature for the victim in this case. They're going to construct their own 6492 signature with their own malicious signer. So they put the 6492 wrapper around their 1271 signature. Their contract, their signer is already deployed. We call isValidSignature on their contract, which says, hey, this isn't a valid signature because of whatever code the malicious person has written into that contract. And then the call data is going to, the DApp is going to use the prepare2 and the call data to call the user's wallet, transfer funds to the attacker's signer, which is probably using a balance2 check to make that Boolean toggle of is valid signature, is not valid signature. And now the malicious signer is going to say, hey, that signature looks good because I've already got the funds. And the attacker can steal and drain the wallet of any user using this system without them even having to use 6492 patterns. They can just take their own 1271 signature. So these attacks have a couple of things in common. The key one is that the permissioned contract, the DApp, is the one also doing the signature verification. And the other big thing, which I've already pointed out, is that the factory address and the prepare2 addresses are arbitrary, and the call data that they're using are arbitrary. So you can put anything in there that you would like as an attacker. We can make this system more secure by inserting a new contract, a signature checker contract, that is going to be the one that makes the call to the proxies or to the factory and handles the 6492 flow. So now the DApp is no longer the message sender, even if there's a batch function, even if there's a multi-call transaction. The message sender that's making the arbitrary calls in the 6492 flow, which are the ones that we're worried about, is now this unpermissioned signature checker contract. So this would alleviate that, those two attack vectors. All right. So like I said, I'm a fellow with Cantina Spearbit. They do provide security reviews, code competitions, bug bounties. Cantina.xyz is how you would find out more about those. I'm going to post these on my Twitter account at @IamChrisSmith. And I've got probably about 1:45. If there's any questions, I can try repeating them, or we can wrap up early. All right. I think that does it then. Thank you.